Now, next topic is density curve. Okay, just you need the definition over here. What is density curve? Just let's read it out. The curve given by y is equal to fx, where fx is the PDF, y is equal to fx, where fx is the probability density function, is called the probability density curve, which gives the graphical representation of the corresponding continuous distribution. Only you need the definition here. Okay, illustration you can means study by yourselves if you want. Up means just right now it's not necessary. Next, go to page number 197. Okay, expectation or mean of a continuous random variable. Sorry. Expectation of a continuous random variable. So what it says, we already studied expectation. Now we are going to look at it from a continuous we had studied it for discrete random variable. Now we will do it for continuous random variable. Okay. For a continuous, you know that the difference between discrete and continuous. I will explain to you in case of discrete only certain values can be assumed. So we were adding those values. Okay. Multiplying it with those points and with those probability mass functions, and we were getting the expectation. And now in this case we have to do integration because in this there will be an interval, and since this is a continuous random variable capital X, the values of capital X, it can assume any value, okay, real value which lies in between that particular range. So for a continuous random variable capital X with probability density function fx, okay, the mean or expectation is defined as Ex, that is equal to, see there is a slight difference, instead of adding the values, multiplying the point with that particular function, probability mass function, we will be now using this particular notation, integration over here, minus infinity to plus infinity. You can tally with that thing when we were dealing with discrete random variables, small x, fx, bx. Okay. So this is how you find expectation in case of continuous random variable. Make an integration between infinity to minus infinity to plus infinity. Those particular points, because they are any values, okay, in that particular range, multiplied with the probability density function dx, provided the infinite integral converges absolutely. Similarly, the mean of the function, now we use another notation. Function x of the random variable capital X will be denoted as, now if instead of small x you have this itself is another function. Say instead of small x you have another function over here. This function and that function will be different. Okay, this function is probability density function, and this instead of x you have a function of x. Okay, so how will you be dealing with that situation? Page number 197. So it will be something like this. E, again function of capital X, that is equal to minus infinity plus infinity, again function of small x, fx and dx. Okay, so this will be the thing for a continuous distribution. We had also studied expectation of function of x also when we were dealing with discrete random variable. Check that video where we made discussions on expectations. So is it clear, this thing? Now we will do illustration. One illustration is there. We will study that illustration from the book itself. We will study. There is no need to write it down and make it unnecessarily a wastage of time. So we have, let illustration, again page 197. Let PDF of a continuous random variable capital X is equal to fx is equal to half or 0. Okay. When is fx half? When the range of x is from -1 to +1, and if it is 0 anywhere else, means other than -1 and +1, wherever be the value of x, it will always be evaluating to 0. And okay, let me write down just only this part. Fx is equal to half when x is greater than -1 less than 1, and anywhere else other than that, anywhere else, it is always 0. Okay. So let's calculate. Then the mean or expectation of x is capital X is. So this range, it means it's a continuous. We are finding expectation of a continuous random variable. So Ex is equal to what it is, minus infinity plus infinity x fx dx. This is the formula. Okay. So that is equal to, now first make the range between -1 and +1. So -1 and +1. So x is equal to, so value of fx is equal to half. See, it's given in the problem. So x dot half dx. And that will be, if you evaluate that, now just make integration. Means, see, now I cannot teach you how to calculate the values of integration and differentiation. Okay, that you have to refer some books here, class 11, 12 books. Okay. So, okay, just I'll give you a view, that is x dot half dx, that is equal to what will it happen. So what will we get? That is equal to, half will come out because it's a constant. So we have only x dx now. So what will it be? X to the power of 1. So it will be now x to the power of 1 plus 1 divided by 1 plus 1. Okay. Now substitute the value of 1 in place of x, and then again substitute the value of -1 in the place of x. So it will be x to the power of 1 plus 1 by 2, that is x squared by 2. So it will be 1 squared by 2 minus of, again, -1 whole square by 2, that will evaluate it to 0. So if you want to learn again integration and differentiation, please guys refer to a class 11, 12 books. Because this example is small, so I was just did it orally, but some complex examples now you have to work out. Okay. So we get the value of Ex is equal to 0. Now let us find out the value of E2x cube. Okay. So 2x cube, now it is a function. See, function of x. So we found out the value of expectation of x when x is a continuous random variable. Now we will find out expectation of 2x cube. Now 2x cube is nothing but a function of capital X. Okay. Just now I've also explained that when the expectation of function of x, the formula was minus infinity plus infinity, then function of x, then fx dx. Okay, where fx is the continuous discrete random variable. So it will be minus infinity plus infinity 2x cube dot fx dx. Okay. That is equal to, now let us set the range -1 to +1. So 2x cube, as it will stay as it is. So fx value will be again half, because it is stated in the problem itself that when the value is x value is -1 to +1, the value of fx will be half. So it will be a half change. So again you will have to calculate. So 2 gets cancelled out. So in the range we have integration of -1 and +1 x cube dx. So what will be x cube dx? How will we do it? So it will be x to the power of 3 plus 1 divided by 3 plus 1. So x to the power of 4 by 4. So 1/4 will come out as constant. Okay. So we have 1 to, so now let us substitute the upper bounds and the lower bound values. So 1 to the power of 4 minus of -1 to the power of 4, that is equal to, again you will get the entire thing as 0. Okay, so this is the illustration. How do we do this problem? Following properties of expectation of a continuous random variable hold as those for discrete random variables. Okay, so let us correlate between some properties of expectation of continuous random variables and discrete random variables. I read those properties. We had already also studied these properties for discrete random variables expectation. So E over of A is equal to A, where A is a constant. Okay, this is property number 1. Next, E over of Ax, that is equal to Aex. Okay, where A is a constant. Then again property number 3, E over of x plus minus y, that is equal to Ex plus minus Ey, where x and y are two random variables. Then property number 4, Ex dot y, that is equal to Ex dot Ey, when x and y are two random variables. Okay, the proofs are not needed. Next, go to page number 198 and 199. Illustration you can do by yourself. Okay, the same thing itself. Variance and standard deviation. Now again for continuous random variables. Now page number 198. So variance and standard deviation. The variance of a random variable capital X denoted by var x is, now the definition is same. Let me rub this thing. The variance of a random variable capital X denoted by var x is defined as, so var x, that is equal to expectation of, so what it was, capital X minus m, the whole square. You remember this thing, where m is itself ex. So this thing once again repeated over here. The positive square root of var x is called standard deviation. Now if I do square root plus minus, only taking this plus will give me the standard deviation, okay? And it is denoted by sigma x or simply sigma, okay? So we get sigma is equal to plus root over of var x. There is a remarks, it is written, the variance describes how widely the probability masses are spread about the mean, that it gives an inverse measure of concentration of the probability masses about the mean. These are all theory, which is called the measure of dispersion. Number 2, as var x is equal to 0, see, I rub this thing. Var x is equal to 0 if and only if, okay, x minus m is equal to 0 or x is equal to m, which means that the whole mass is concentrated at the mean, okay. You know what is x, you know what is m. So var x will be 0 if x minus m is 0 or x is equal to m. Okay, now we will study some theorems now on this. So what are these theorems? Let's just go for them. So var x theorem number 1, page number 199, okay. Var x, that is equal to e x squared, already you have done this for discrete random variables, ex the whole square, okay. Theorem number 1. Theorem number 2 states, var, this is also you have done for discrete random variable, ax plus b, that is equal to a square var x. Theorem number 3, var k is equal to 0, where k is constant. And then theorem number 4, var x is equal to expectation of x minus 1 minus m minus 1, okay, where m is the mean of x. No proofs needed. No proofs needed. So you please study these properties, 4 properties. I've just written what is whatever image is been sent. You have to not just I'm stating them because already these things are covered before. But you have to now think about them and have to remember them. Now we will study the last illustration, okay, and 2 examples, one example inside it, and then we will be closing this statistics portion, and again we will go on to pattern recognition, that is Bayesian decision classifiers and normal density, univariate, multivariate, all these things, covariance matrices we will study. And they will become very easy for you to learn now because already I have gone through those terms. Okay, this video is getting longer, so I close this video and I go for the next video and explain that those problems, okay.